All right, so now we're going to use ice tables. Ice tables. All right, now, ice tables. What are ice tables for? Ice stands for initial, C stands for change, and E stands for equilibrium. We're going to use this so many times you don't need to necessarily write that, but I stands for initial, C stands for change, E stands for equilibrium. All right, what are we using ice tables for? We're using ice tables to, so I like to kind of explain what we're going to be doing first, then basically we're just doing practice problems. There isn't a whole lot of concepts left. You already understand the concept of equilibrium, Q and K. So now we're going to be doing different sample problems to determine the value of Kp or Kc, so really just K, equilibrium constant, and to determine equilibrium concentrations. But these problems are a little trickier than ones we've already done because there's going to be a change. So the question will say you'll have this many moles initially. How many moles are going to be found at equilibrium given the following K value? Or they won't give you the K value. You have initial moles. You have to find your equilibrium moles and then set them up to solve for K. So that's where the C comes in. There's a change. So you have initial conditions, a change, and then equilibrium. So that's what we're going to be using these for, and the only way to really learn this is to do a whole bunch of practice problems. So we're going to do about 5 problems right now, and I'm going to assign a bunch for homework. And then we have more stuff to do. All right, so here we go. These are the types of questions that would be on the AP test. What we've learned so far, maybe, these are the ones they focus on. All right, here we go. We have a mixture of 0.5 moles, so write this down here. So we have a mixture of 0.5 moles of H2 and 0.5 moles of F2 in a 2-liter flask at 50 degrees, nope, at 530 degrees. Okay. The equilibrium constant is Kc is equilibrium constant. Oh, sorry, I gotta give the reaction. For H2 plus F2 yields HF. We need 2 there. This is gas, gas, gas. So the Kc for this reaction is, well, I guess I'll just write it here. So K is equal to 52.1. I want to calculate the concentrations of H2, F2, and HF at equilibrium. So I'm going to put, I'm going to use this space. How do I write? I'm just going to write this. Calculate the H2, bless you, F2, and HF concentrations at equilibrium. Okay. All right. So K is 52.1. Alright, so I'm going to rewrite that reaction here. You need space underneath your reaction. So you're going to need like 3 or 4 lines underneath. So if you need to rewrite the reaction, go ahead. H2 plus F2 yields 2HF. Alright, so they give us initially what's going on. You have 0.5 moles of H2, 0.5 moles of F2 in a 2-liter flask. Okay, so that's initially, then it reacts. And it reaches equilibrium, but we don't know anything about that, except we know the constant. Do they have any HF in the problem? Did they give us any? Any product at all? No. So initially we're going to say 0. We don't have any. Here's where the ice table comes in. You write ICE down the left side. So learning like the method and doing this over and over is half the battle. So initially, underneath H2 and F2, we're going to write down initially what the concentration is. It's not 0.5 and 0.5. What is it? 0.025 or 0.25? 0.25. Okay, so 0.5 divided by 2. So I'm not showing that step, but because it's a 2-liter flask, 0.5 divided by 2, we got to get 0.25. I'm going to leave my molarity there. A lot of times in the book, they will not label the unit, and that confuses students, because if you think that's moles, it's going to kind of mess you up down the road. So 0.25 and 0.25. We have the same amount of both. We have 0 for HF. That's initially. Now, change. How is this reaction going to change? If we have products, if these two reactants are going to form products, then what's going to happen to these numbers? Are they going to get smaller or are they going to get bigger? Smaller. Why? Give me a word. They're being, that's what C. Consumed. Right. So the way we do all of these problems, this is just our first example, but if you really pay attention, it really helps moving forward. The way we do all these problems is you use the stoichiometry rate, the mole ratio, stoichiometry here, stoichiometric coefficients, to figure out the change. So this is a 1-to-1 ratio. So whatever change happens here, the same change is going to happen here because it's 1-to-1. What's going to happen to this change? It's going to be double because it's 2-to-1. So that's what balancing is all about. So if 1 mole of this reacts, you're going to get 2 moles of this. That's the 1-to-2 ratio. So change is always going to have unknowns. And the unknown is, I use X. So H2 is going to decrease by a certain amount. We don't know what it's decreasing by, so we're just going to put minus X. That X represents the number of moles per liter. H2 is going to decrease. So this is how many moles are going to react, right, are going to be consumed. Think of it that way. This is the same, minus X. Whatever change happens here, the same change happens here because it's 1-to-1. What's this going to be? Plus 2x. I like to put the plus because it helps you really understand. These are decreasing, this is increasing. So what would we write for the equilibrium concentrations, I don't know, with respect to X or using X? What would be the final, remember, so this is like initial change and final. So what would this equilibrium concentration be? How would we show that using these two? Yeah, just 0.25 minus X, that's it. 0.25 minus X, 0.25 minus X. And then this one would be 0 plus 2x. You don't have to show that. You can just put 2x. It's 0 plus 2x. So what some students, Maddie, can you see? All right. Next one I'll do higher on the board. What students sometimes get confused about is, why was that funny? She's in the back and I got all this stuff in the way, so it's easier to see up here. Bunch of jerks in here. So anyways, the kids in the past get confused with, what do I write here? How do I get it? All you're doing is combining I and C. You're combining these and putting them into one step. That's it. Okay. You're solving for X. You know the K value. How do we find K? Products over reactants. So everything we've learned up to this point is to help you understand how to do these problems. So hopefully you understand the shifting, the Q, the K, how to set it up for K and Q. So now you're going to use the equilibrium step here, the final step, plug these in for the equilibrium expression, K equals products over reactants, solve for X. We don't need the quadratic equation here because this thing isn't squared. If this guy starts to get squared, then it screws everything up, and then we got to do that. But we don't have to here. You'll see. So go ahead. You guys are all in pre-calc, calc, whatever. You're mathematical geniuses. Let's go. Solve for X. Products over reactants. Solve for X. Use the equilibrium concentrations in your equilibrium expression, obviously. So 52.1 equals products over reactants. Solve for X. Go ahead. So I'm just going to erase this so I have more room. I think I'm going to get a new marker for this. That's how this guy works. That's nice. Let's see who remembers. So once you solve for x, then you can answer the question. Because that's not the answer. The answer is the equilibrium concentration of H2, F2, and HF. Dylan, you're forgetting something. Pat, you're forgetting something. Ah, there you go, Slade got it.
I'm not done with it.
You're forgetting something.
I wasn't done with it yet.
Oh, alright.
You didn't forget it.
I'm still.
You guys, you didn't set up your, no one's doing it.
What?
Why, how can you go back and do it? Do it initially.
What?
What did you say you forgot?
I haven't distributed everything yet.
No, you don't need to, no, not that. That's
I'm not like being a jerk, man. I'm like being serious.
I know you're not. Ah, Steph got it. Let's see. Steph's the only one to remember to do it.
Oh, it's probably like converting something.
How would you, forget the numbers for a second. Let's just use the chemical formula. What would the equilibrium expression be? Forget the numbers. Plug in, H2, F2, and HF. What would it be? It would be HF squared. So HF is 2x. So it's 2x squared. That's a really important step there. Because there's two HFs. So remember when we wrote, that's when we learned, so the first thing we learned about equilibrium expressions is if there's a 2 in front, you square it. If there's a 3 in front, you cube it. So even though there's 2x, you're taking into account the 2, you have to square it in the equilibrium expression. So it's 2x squared over 0.25 minus x squared. Because it's 0.25x, or 0.25 minus x times 0.25 minus x. And you don't have to do, what is that, FOIL or whatever, you don't have to do that. Just combine it, it's squared. And if the top is squared and the bottom is squared, well, sort of, you got to do something. Pat's looking at it. It'll jump out at you. You have a square on top, you have a square on the bottom. Dylan, what do you do to get rid of the square? Take the square out, right? How do you do that? Right, but if you square root that side, you got to square root the other side. Good.
Dude, I got some.
Alright, so
Okay, Pat. You square root this whole side? I decided that I don't know what the square root of 52 is. What's gonna happen? Yeah. It'll be.
Not that it really matters, but it kind of just matters to me. I mean, it does matter, I think, sort of. I always get confused with some of these mathematical rules here. I always do that. I always put the 2x in parentheses because the whole thing is squared, not just the x. So I always just keep parentheses around everything. It just makes life easier. So, but anyways, you guys are all at the same spot anyway. So if we take the square root of both sides, you can keep working. I'm just going to put the next step. That's 7.218 equals 2x over 0.25 minus x. Now you have to cross multiply, distribute, and all that fun stuff. Solve for x, or get the x on one side, numbers on the other. Anybody have an x value yet?
Yeah, 0.195.
Yeah, I got 0.196. Good. 0.196. So,
Yeah.
honestly, I know everybody can do this, so if you made a mistake, that's fine, but just be careful when you cross multiply here. I'm just going to write out the next step. 1.8045 minus 7.218x equals 2x. So then you would add 7.218x to this side, 7.218x. So you would get 1.8045 equals 9.218x. Divide by 9.218. Divide by 9.218. X equals 0.196 molarity. So that would be X. That is not the final answer. These problems are long, okay, and this is not that hard. This is not like a hard one. But it's just the first one we did. So why are we doing this practice problem? So you see how to set up the ice table, how to do the change row, right? Minus x plus x based on coefficients. And then there's a fairly tricky algebra, I guess. So you solve for x, plug it back into your equilibrium constant, or your equilibrium row. So 0.25 minus 0.196 for H2 and F2, and then 2 times that number is for HF. That's your final answer. So for H2, it would be H2 and F2. It would be 0.25 minus 0.196, so that equals 0.054 molarity, right? Moles per liter. That's for the 2 reactants. And then for HF, it would be 0.196 times 2, and that would be 0.392. That is a pretty typical equilibrium question, where they give you the initial values of the reactants, and they ask you to solve for equilibrium concentration. They have to give you the K though, otherwise couldn't do that. Questions? So what you're supposed to get out of this problem is how to set it up, how to solve for x, and then when you're all done, get the equilibrium concentrations, and does it make sense? It should. These two are going to decrease by the same amount because it's a 1-to-1 ratio. This will double, so that's why you multiply by 2, so that's why these numbers are what they are. Question before we move on to another one. Okay. Apparently you need the book for another one. Page 644. Practice exercise on the bottom. Page 644, practice exercise. I just found this morning, actually. And now you don't have one.
Oh man, don't get it. No, we can find it. We can find it.
Oh, this banana peel still sitting.
Yeah, Dylan never picked it up.
I think we should put it on the heater and make it. That's what you do.
644. Chapter 14 messed up.
What?
You get the messed up one, sorry. This may not even have a page 644.
I hope it does.
It doesn't. It goes from 637 to 638 to 671. Okay. All right. So just get it for one of these guys.
Sitting right next to me.
All right. So practice exercise 644. Right at the bottom, above example 14.10. So above example 14.10, it says consider the reaction in example 14.9, so you have to flip back. Starting with a concentration of 0.4 moles per liter for HI, calculate the concentrations of those at equilibrium. So the reaction is on page 643. I can write it on the board, I guess, Earl.
No, I'll don't let them. No.
Well, go ahead, you guys just, it's very, very similar to what we just did. So I want you to copy it into your notes, so go ahead. I'll put it up here anyway, because I'm going to go over it.
For every minute.
Yes.
All right, take a break. Yeah, I would get up more.